Welcome to Chapter 2, From Molecules to Qubits. Chapter 1 left us with a problem and a promise. The problem is that the exact electronic wave function lives in a space whose dimension explodes. The promise is that a quantum register spans such a space using only 1 qubit per spin orbital. What sits between the two is a translation job, and it is not a formality. Electrons are fermions. Swap 2 of them and the wave function changes sign. Qubits have no such property. Qubit 3 and qubit 7 are labeled, distinguishable objects, and nothing in the algebra of Pauli matrices knows about the exchange of identical particles. Start by throwing away a habit. In the first quantized picture, you write a function that says where electron 1 is, where electron 2 is, and so on. That framing is already wrong, because electrons have no identities to assign. All the antisymmetrization machinery exists to undo a labeling you should never have introduced. Second quantization removes the labels at the start. Fix the spin orbitals from Chapter 1 and think of them as slots. A configuration is described by saying, for each slot, whether it is occupied. That is an occupation number state, and the space of all such strings is Fock space. We move between occupation number states with 2 operators per slot. The creation operator fills a slot and gives 0 if the slot is already occupied. The annihilation operator empties a slot and gives 0 if it is already empty. Applied to the vacuum, products of creation operators build any configuration, up to a sign, and that sign is the whole point. Read the algebra. Creating 2 electrons in the opposite order flips the sign of the state. That is exactly the antisymmetry a Slater determinant was built to enforce, except nobody enforced it. Set the indices equal, and a creation operator squared is 0. In this language, the electronic Hamiltonian takes a compact and completely general form, a 1-electron sum plus a 2-electron sum. Every molecule differs only in the numbers. The 1-electron operator removes an electron from one spin orbital and puts it into another. It is a hop, and its coefficient collects kinetic energy and attraction to all the fixed nuclei. The diagonal case is the number operator, an energy cost for merely occupying that slot. The 2-electron operator describes 2 electrons scattering into new orbitals, with a coefficient arising entirely from Coulomb repulsion. The integrals are classical input. The ground state search is the quantum job. We now have a Hamiltonian built from creation and annihilation operators and a machine built from qubits. The temptation is to declare victory. Occupation numbers are bits, and Fock space has exactly as many states as a register of that many qubits. The states do match. The operators do not. Qubit operators acting on different qubits commute, always, because they act on different tensor factors. Fermionic operators on different modes anticommute. So a naive bit for occupation assignment gets the bookkeeping right and the signs wrong, and the signs are the antisymmetry of the wave function. Lose them, and you simulate a different physical system. The oldest solution is also the most transparent. Assign the modes a fixed order, map each mode to its own qubit, and define the annihilation operator as a product of z operators on every qubit below it, times a local lowering operator. The local part does the obvious job of emptying the qubit. The new ingredient is the Jordan-Wigner string. Z is diagonal, returning +1 on an empty mode and -1 on an occupied one, so the string multiplies the state by -1 for every occupied mode to the left. It counts electrons below and manufactures the parity sign. Nothing is free. A fermionic operator that acts on a single mode becomes a qubit operator acting on many qubits. A hopping term between adjacent modes stays compact. A hopping term between distant modes drags a string of z operators across everything in between. This is the locality cost, and it is practical rather than aesthetic. A Pauli term acting on many qubits takes a deeper circuit to implement and more measurements to estimate, and the string length grows with the number of orbitals. Alternative mappings trade the cost differently. Bravi-Kitaev is the best known. growing logarithmically rather than linearly. Abstraction has gone far enough. Take 2 spin orbitals and 1 electron. With only 2 modes, there is no 2-electron term, since 1 electron cannot repel itself. Mode 0 has nothing below it, so its string is empty. Mode 1 carries a single z for the number operators the strings appear twice and cancel, because z squared is the identity, so occupation maps onto a single z per qubit. For the hopping term, the string survives, and the imaginary parts cancel to leave 1/2 of x plus y the whole Hamiltonian becomes a weighted sum of Pauli strings. The example that runs through the rest of the series is the hydrogen molecule in a minimal basis, and now we can size it exactly. A minimal basis puts one s-type function on each hydrogen atom, so there are 2 spatial orbitals. Each holds spin up or spin down, giving 4 spin orbitals, and Jordan-Wigner assigns 1 qubit per spin orbital, so the molecule maps onto a 4-qubit register. Chapter 1, counting, applies directly. 2 electrons in 4 spin orbitals gives 6 determinants. The register spans 16 states, so most of it describes the wrong number of electrons. This section is the centerpiece. We build the Jordan-Wigner operators for 4 modes as explicit 16 by 16 NumPy matrices, and then test them, because a mapping that gets the signs wrong is not obviously wrong to the eye. Every anticommutation relation is satisfied with deviation exactly 0, not merely at the level of rounding, because the matrix entries are drawn from 0 and plus or minus 1. The annihilation operator squared vanishes for every mode. The number operator has eigenvalues 0 through 4 with degeneracies 1, 4, 6, 4, 1, exactly the binomial coefficients. Let us recap. Second quantization replaces labeled electrons with occupation number states over fixed spin orbital slots and replaces antisymmetrization with an algebra. The electronic Hamiltonian becomes a 1-electron hop term and a 2-electron scattering term whose integrals are classical input. The mapping problem is that qubit operators commute where fermionic operators anticommute. Jordan-Wigner repairs it with a string of z operators that counts occupied modes below at the cost of Pauli weight growing with mode separation. Weight 2 for an adjacent hop, weight 4 across 2 modes. Hydrogen in a minimal basis becomes 4 qubits. Next, VQE, the algorithm.